Welcome back to Why This Universe. In our last episode, we heard from Adam Riess, who won the Nobel Prize for discovering that our universe is expanding at an increasing rate. Today, we're picking up on that conversation to ask Adam what he thinks of what's been dubbed the crisis of modern cosmology. The fact that when you measure the expansion rate of our universe in two different ways, you get two different answers. And it might be because our model of cosmology and of how the universe has changed over time is mistaken or wrong in some way. So stick around for the conversation. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. Recently, we had Adam Riess on Why This Universe to talk about the discovery of dark energy. But in that interview, we didn't get a chance to talk with him about his more recent work on what has become known as the Hubble tension. This Hubble tension comes down to the fact that when you measure the current rate that our universe is expanding, as his group has done, you get one number. And when you try to infer the rate of expansion from measurements of the cosmic microwave background and other things, you get a different, smaller number. This tension seems to mean that either one, something is going wrong with one or more of these measurements, or two, something must be wrong with the standard cosmological model itself. That latter possibility, of course, would be a very big deal. And today we have Adam Riess back with us to talk about the Hubble tension and what it might mean for cosmology. Thanks, Adam, for coming back on.
Thank you for inviting me again.
Let's just start by talking about what are the steps you take to measure the local rate. By local, I mean in the surrounding millions of light years, the rate at which the universe is expanding today.
Sure. So the quantity we're trying to measure, called the Hubble constant, measures the present expansion rate of the universe. And so when we look out at a distant object, the fact that it's red shifted, the wavelength of light we're receiving is longer than the wavelength of light emitted, tells us that the universe is expanding. And by measuring distance to that object, we are finding out how long ago that light was emitted to reach us. So we're finding out over what time that expansion has occurred. It's a rate. And so it's telling us the expansion rate of the universe. So all you need to do is to be able to find a distant object, measure how far away it is, and measure its redshift. Now, the redshift is the easy part. If you take the spectrum of a distant object and you can recognize some features in its spectrum due to the transition that happens, certain atomic elements in the laboratory, then you easily measure the redshift. And as long as it's bright enough to collect photons of light, you can do that. Distance is the hard part. That's where all the work comes.
Right now, what are the astronomical objects out there that we use to get the best value for those distances, the most reliable, robust value for those distances, and therefore the Hubble constant?
Right. So I would say, while there are multiple ways to do this, at least my favorite way, and maybe because it's what I've worked on, or, I think most people would agree is probably the most precise, is to find a distant type 1a supernova. You need to measure something far enough away, because if it's too close, you won't even see the universe expanding. You'll see some other phenomenon.
Just a random motion, yeah.
Yeah, I mean, if I looked at the Andromeda galaxy, right, I would actually measure that it's not even moving away from us. It's moving towards us. There's a gravitational attraction between us and Andromeda. And so I'd measure a negative value for the Hubble constant. So I need to get out into deep space where the effects of the attraction from nearby objects is small enough or averages out enough. Only very few objects are really luminous enough that I can see them that far away. And one of them is the type 1a supernova. The problem, though, with the type 1a supernova and other things of that type is I need to know how luminous one really is so I can judge from its brightness how far away it really is. It's like, when you cross the street, you at night, you see the headlights from a distant car, and you make a mental calculation how far away the car is based on how bright the headlights appear. Now, you can be fooled if those headlights were not really from a true car, but a little toy car. And if that's a little toy
Sure.
car, they're not very bright, and that means the car's right up upon you. So we need to be able to, we say, calibrate the luminosity of at least one, hopefully more than one type 1a supernova. And so what you need to do is, get a tape measure and run it all the way out to a type 1a supernova. Of course, we don't have a tape measure that goes that far. And so instead, we build a chain of measurements that is called a distance ladder. It starts with geometry. For example, parallax. We're all familiar with parallax. Your two eyes observe a nearby object from two different vantage points, and your brain calculates the change in the angle it sees for that nearby object and does a mental calculation of how far away that object is.
This is just ordinary depth perception, right?
The ordinary depth perception, but it works by the principle of parallax. To see and measure parallax effectively for something far away, you need to have your two vantage points be themselves separated more. And so the biggest separation and vantage point we get is when the Earth goes around the sun. We can take an observation of an object from one position where the Earth is on one side of the sun, and then 6 months later when it's on the other side, as though we had two eyes, and we were getting depth perception to some star, let's say, relative to something infinitely far away. The problem is that stars are really far away. They are so far away that even at those two different vantage points, the angle becomes very small. And so it's really only been in the last decade or so that we've been able to effectively measure parallaxes throughout the Milky Way galaxy.
All right, we start with parallax, and then we build to what's next.
Right. And then you need a kind of star whose luminosity is very uniform or very predictable itself in some way. Now, if there was a type 1a supernova in our Milky Way galaxy, you'd measure the parallax to it, and that would be your whole distance ladder. But they're so rare that there hasn't been one in our galaxy in hundreds of years. And so you have to instead find a kind of star that is common enough to be seen in our galaxy many times, and yet also can be seen in other nearby galaxies that perhaps did recently host a Type 1a supernova. And I think the gold standard for these kinds of measurements has been the Cepheid variable, which is a supergiant star first recognized over a century ago by Henrietta Leavitt, who noticed a peculiar phenomenon when she looked at a cloud of stars called the Small Magellanic Cloud, which she presumed correctly were all far away from us outside our Milky Way, but at a shared common distance. She found that she found that some of these stars were varying in their brightness over weeks and months. But what she noticed in particular, and this was the key breakthrough, was that the period or interval between peak brightnesses for these Cepheids correlated very strongly with how bright they appeared. And since they were all at the same distance, really meant correlated with how luminous they were. And so this produced an outstanding way to measure relative distances. That is, you find one of these variable stars and you measure its light curve, the time it takes to go from peak to peak again. And that refines your understanding of how luminous that star is. So if you can measure the parallax of some of those kinds of stars in the Milky Way, you have calibrated their true luminosity. And then when you see them in nearby galaxies that hosted Type 1a supernovae, say with the Hubble Space Telescope, then you can measure the period and use this calibration that you have produced in the Milky Way to measure the distance to those galaxies and then calibrate the true luminosity of those Type 1a supernovae, and then look for those Type 1a supernovae further away into the deep expanding universe. And so this is a network of measurements called the distance ladder, which is, it's not even based on physics. It's just geometry and just the fact that two things at the same in the same galaxy or the same distance from us to them. And so it's very, very logical. And as long as you do careful measurements, gives you a very good way to measure the Hubble constant.
Okay, so when groups like yours take the distance ladder, including parallax, Cepheids, and supernovae, what kind of values do you get for the rate at which our universe is expanding today?
Yeah, so I would say state-of-the-art measurements today using, the Hubble Space Telescope throughout the chains in this, making the best measurements in the near-infrared, calibrating dozens of Type 1a supernovae using modern supernova data. When you do all the steps as best you can, and just to be clear, this work has gone on for decades. It is built on generation after generation of improving these steps. But when you do this at the state-of-the-art level, you get an answer of about 73. And if you do very careful measurements, keeping track of uncertainties and covariance and complexities, you get the answer with an uncertainty of about plus or minus 1. So let's say 73 plus or minus 1.
73 plus or minus 1 kilometers per second per megaparsec. So for our listeners, that means for every megaparsec or every million parsecs, or roughly 3 million light years, 2 points are separated. They are moving apart. They're growing. The space between them is growing by 73 kilometers every second.
Correct.
Good. All right. So we've got one way of measuring this. Now let's go to measurements of the cosmic microwave background and other kind of cosmological ways to infer the Hubble rate. How is that done, and what are they finding?
Right. Well, that's a good question. So now we're to the other end of space. So we're back at the beginning, shortly after the Big Bang, and so we have this hot primordial plasma, which is kind of rippling. And if you've ever seen a picture of the cosmic microwave background, you see these hot spots and cold spots, and physicists are able to calculate the size of those hot spots and cold spots, their physical size, by using physics and by understanding or having a model of the composition of the universe at those times. So they use the model, lambda CDM. It returns to them a calculation of the physical size of those spots. Then they look at the angular size of how those spots actually look on the sky. And when you've measured an angular size and you know the physical size, that describes a triangle. It measures a distance. And they know also from first principles the redshift at that point in time when the cosmic microwave background streamed out to us. This is called recombination. And so they essentially have a distance and a redshift, which, by definition, tells you the Hubble constant, or at least it tells you, I would say, the average value of the expansion rate over the total time that the light has been reaching us. But if you, again, use this model of lambda CDM to describe the universe, you could separate out how there have been changes in that expansion rate over time, how matter and dark energy would have changed that, so that you could remove those effects and figure out what is then the actual value of the Hubble constant today. So you can predict today's Hubble constant, and the answer they get is 67 plus or minus 0.5. So on the one hand, you say, hey, that's not too bad. We're only off by 10%. This is, like threading a needle from the other side of the universe, going from the beginning to the end, understanding everything in physics. You're only off by 10%. But, we're pesky, us scientists. When we think we've made a very good measurement 2 different ways and they disagree by, 5 times the error bar, we say, okay, well, close, but no cigar. This is not exactly what should be. Something has to give here.
Good. So we've got a direct measurement of the expansion rate today, which your team and others have done. We get 73 plus or minus 1. We take our best cosmological model, apply it to the cosmic microwave background data and all that stuff, and we infer that the number should instead be like 67 plus or minus a half. These don't overlap. They're in strong statistical tension. What's the current statistical tension? How many standard deviations?
It's probably more like 6 sigma at this point.
6 sigma.
6 times, yeah.
And everyone in physics would agree that 5 sigma you could call discovery if you're really confident you've done everything right. This is overwhelmingly statistically significant.
Correct.
If something's going wrong here, it's unknown systematic, right? Something's going wrong that we haven't figured out yet. It's not just a merely not enough statistics. Yeah.
Right. So, yeah, let's discuss that for a minute. So, I mean, this has been a slowly evolving train wreck, sort of, so to speak, in that, nobody just woke up one day and said, my gosh, Six Sigma. I mean, this has been building for about a decade.
Right.
Initially it was 2 sigma, 3 sigma. The measurements got better and better. But, what also happened was other experimentalists came and measured this quantity, either taking the data we had collected and doing the calculation themselves, to collecting their own data. In the case of the cosmic microwave background, you have other ground-based CMB experiments like ACT and SPT, who would observe with their own equipment and make their own inference. We're getting the same answer, sometimes even lower. I think most recently I've seen SPT and ACT together, independent of Planck, are more like at 66, 66 and a half.
Even a little lower, yeah.
Right. And then in the local side, you have people substituting different steps in this distance ladder, distance network, instead of Cepheid variables using, the brightest that red giant stars get, or using a different kind of pulsating star called Miras, or different kinds of tools, maybe not as good as Cepheids, but good enough to do cross checks. And then, instead of type 1a supernovae, using type 2 supernovae, using surface brightness fluctuations, instead of using parallax, using other geometric measures, detached eclipsing binaries in nearby clouds. And the answer ranges some from 70 to 75, I would say, but they are all above the value you get from the cosmic microwave background, and they are all internally consistent. Our answer is the most precise because we have the most data. We've calibrated the most type 1a supernovae. We have the most geometric anchors. We probably use the most Hubble Space Telescope and James Webb Space Telescope time. But within this range, it's systematically off in one direction for anything that's precise. And so, it is, and likewise, the CMB has, been confirmed many ways. So it seems, less and less likely that it could be systematics, which has, I think, really raised people's interest in this problem.
Good. So we've had other episodes of this podcast where we've talked about the Hubble tension before. We had Dan Skolnick from your own team on before, but we also had Wendy Friedman, and she has a very different opinion on this. So she heads one of the other big groups doing these like local Hubble measurements. Can you describe what she finds, what you find, and where you agree, where you disagree, maybe why, possible reasons for the disagreement?
Sure. So I would say, there's probably, about a dozen groups or a dozen studies that have made this measurement. And Wendy Friedman's group of the dozen, I would say, gets the lowest value of any of them. Still, higher than the cosmic microwave background value.
What's her number now?
Yeah, her number is 70.4. Is her latest number.
Okay. So about halfway between where the cosmic microwave background says and where your group says.
And with larger uncertainties because her sample of type 1a supernovae is smaller.
Yeah.
And so formally her results are consistent with either. They're consistent with the cosmic microwave background, and they're consistent with the other local measurements. So, at some level, as experimentalists, you go, okay, I expect that, right? I mean, if it's consistent with both, that doesn't, it's inconclusive about this.
Yeah.
Now, the reason that her result is lower is there are 3 rungs to this distance ladder, 3 steps. And if you, at this point, go through the first 2 steps, which is to say, well, what distances do you get to nearby galaxies which host a type 1a supernovae, then we're in excellent agreement. We get the same distances using different methods. That's very powerful. However, what we've seen is she has a smaller sample of type 1a supernovae that she's calibrating. And if we look at that sample of type 1a supernovae within our larger sample, then our answer also skews lower, which is to say that there is variation in the individual supernovae. This is expected. They all have fluctuations. And her subsample is a low draw of the Hubble constant from our larger sample. And that happens as well. One doesn't normally replace the big sample with the small sample. One uses the small sample as a cross check on the big sample, and we get the same or more or less the same answer within that subsample. But, we all know that you get better, more accurate results by using larger samples. You reduce fluctuations. It's a little bit like if you've ever heard a study, oh, coffee is good for you or bad for you, or wine is good for you or bad for you. Often, some of the fluctuations in that are from smaller studies of smaller populations, which, can be consistent. But you want a larger sample to reduce those fluctuations. And so when we look at the largest samples, then that's what we see. I think people, looking for a way out of this problem, will focus on, oh, what about the lowest measurement that's ever been made? But, that's not normally what we do when we look at the best results we can. We look at the combination really of all experiments. And so if you fold in our measurements and Wendy's measurements and the other 11 groups all together, you're still at 73 and the error bars get even smaller and you're up to 6 or 7 sigma. And so, I don't think we can just, ignore the other 10 or 11 experiments, especially ones with more data, and focus on one that is formally consistent with everything. It doesn't tell us a lot at this point about the reality of the Hubble tension.
Are there any, reasons given by Wendy Freeman's group or anyone else's group for like why some of the supernova might be more reliable than others? Maybe some of the ones with that give a smaller number of the Hubble rate might be more reliable than those that are giving a higher number. Are there any proposals for that might try to reconcile this whole picture?
Right. I haven't seen that, nor have I seen a good description of what's very important in an experiment always is to define what your selection criteria are, because you don't want to have a biased result. And so you say, okay, we're going to include every supernova out to a certain distance, or every supernova observed up to year such and such. And so in their case, they have a set of, I think, 24. And I have not found a clear definition of why those 24 and not, for example, others. Even using their method of tip of the red giant branch, there's actually 35 in the archives of HST and JWST. And if you use all of them, then you get an answer that's a couple clicks higher than her result, meaning the ones that she's not using get a good deal higher Hubble constant.
Right.
That can happen from luck, but I'm unaware of any explanation. But, again, when you have a lot of measurements, a lot of different groups, by definition, there will be a lowest and a highest. We could just as easily focus on the group that gets the highest result, which is probably 76, and that's coming from DESI, the distance ladder that runs through the fundamental plane of galaxies. And the fluctuations happen in both directions, I think, but people tend to focus more on the ones that suggest a way out.
5 or 10 years ago, I think people knew about this tension, but I would say most people thought it would probably resolve itself if you gave it enough time. It's gotten harder and harder to think that way now. I think you visited the University of Wisconsin this spring and we talked about it. And, I'm kind of been a reluctant adherent to this position. It really looks like something weird is going on here and that some sort of new physics might be required to explain it. That being said, I'm a theorist and I've looked at the ways that you can add new physics to explain it, and it's all really weird, right? Like, There's nothing particularly vanilla that can explain it. You need to do some pretty radical things. Some of the most popular ideas, among others, are that maybe there was a second kind of dark energy that was abundant in the early universe and it since disappeared. Maybe there were relativistic particles, what we call dark radiation, that interact among themselves a lot.
Yes.
Especially if they have some sort of like masses that are like carefully chosen, what we call a mass threshold. This was proposed by my former student, Asher Berlin, and his collaborators. I really like that idea. There are a lot of papers on like varying electron mass, like models, like a lot of pretty radical things. Do you have any favorites? Does this go into your thinking at all? Or as an observer, do you try to keep arm's length from what the theorists have to say about the problem?
Right. I mean, I definitely pay attention to it. Go to talks. I'm very interested in what could cause this, and the one part I sort of sometimes have a different perspective than maybe some theorists when I see these models is the subject of fine tuning. I think this is a funny perspective that people have on fine tuning. They'll say things like, "Well, I mean, that is such a fine-tuned model, and it requires just so dark energy to be here and at some early time or a particle." And I think, well, what's the alternative? It's lambda CDM. Is that not finely tuned lambda? I mean, in our previous episode, we talked about how that it's 120 orders of magnitude off of what's natural, and it requires you to go pretty far at the simplest is to speculate that there's 10 to the 500 universes, a multiverse, and our values anthropically selected. So there's no way out of cosmology that doesn't end up with some finely tuned situation. And so at that point, it's a question of taste. I would almost say, well, is this more finely tuned than that? Can this happen? I think we all know that the cosmological model we have it's not Maxwell's equations. It's not something that we can understand from first principles. And so I think we have to be flexible enough to say, we want to try to figure out what's going on, but we have to pay even closer attention to reproducible measurements because like we saw in 1998, you have an expectation, that omega matter should be 1, and then you see something very different, and we really make the most durable progress in this field by paying close attention to reproducible measurements.
Yeah, I agree with all that. It's just a matter of the more unlikely you think a theory is to be true going into a measurement, the more compelling that measurement has to be to convince me that it's probably true. And we're
Sure.
reaching the point where I've been kind of drag kicking and screaming into
Yeah.
this perspective, but I'm pretty close now. I'm pretty much there.
Yeah, I mean, I think, look, we wouldn't be talking about this if we knew what the answer was, right? If
Sure.
we're like, oh, well, we just twiddle the model in this way, and now everything fits, yay, right? We'd be kind of moving on through that. I think, this is a thorny problem. There's no question about that. But I think perhaps nature could be creative, and maybe we haven't caught up enough to our creativity.
Sure.
I mean, anything from new physics in the model to, some fundamental way in which we misinterpret observations or measurements on the sky, which, I'm not even quite sure what that would be exactly, because otherwise I would, tell you the answer to that. But again, going back to the way we were able to get our heads around publishing the results from 1998 of the accelerating universe, at some point you say, hey, we've done this experiment, we've done it carefully, it's been reproduced. We all now need to wrestle with this. I'm not interested that much in, cherry picking this particular result. Maybe we could get out of it if we ignore these 10 data points or these 7 studies or whatever and just grapple with what's in front of us. And I think that's sort of where we are today.
So if I go to a cosmology conference today and I go around and ask people what they think about this, the most common answer I'll get is kind of a wait and see. Like they're intrigued. They think it could maybe be a sign of new physics, but you would not find many at all who would be convinced it is. What would have to happen? What observation or other development would have to take place where we could kind of all more or less agree that new physics, exotic physics beyond the standard cosmological model is at play here? What would that require?
Yeah. I mean, when I look at the history of science, other times where there was, what turns out to be a critically important clue that something is breaking down. For example, look at the precession of Mercury, known from 1850 to 1916, not resolved until, general relativity comes along and explains it. Look at the solar neutrino problem, seeing oscillations in the numbers of neutrinos. Look at many things. And it's rare that we sit there and say we are utterly convinced this experiment is right without knowing what the theoretical understanding is. And so I think the history of science shows that people stay on the fence until they have an understanding of what's going on. And so, I think that we could end up seeing that as well. Some of the people I have a lot of respect for in the world of the cosmic microwave background and theorists will say, I've put this problem in my parking lot. I can't explain why it is. I don't want to disrespect the measurements because you sort of do that at your own danger. But they don't know what's going on. I get that. I think I would love, for example, to see LIGO measurements, a totally independent way of measuring with gravitational waves. But if LIGO confirmed the same thing, I think you would still see a lot of people saying, "Yeah, but I don't know how to do this. I don't know how to
Right.
explain this. I don't know." And so, as I said, I don't think going back to the precession of Mercury, people speculated that there was another planet in between Mercury and the Sun called Vulcan, which they looked for decades. And if you can't be convinced on measurements of the precession of Mercury that is real, I mean, that shows you the power of the struggle we have to accept results that we can't explain. And so maybe we live there for a while.
Why This Universe is produced and edited by me, Shalma Wegsman, and our co-host is Dan Hooper. Dan is a professor of physics at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you like our show and you want to support us, you can join us for as little as $3 a month on Patreon. There you can also get access to exclusive Ask Us Anything segments where you can directly ask Dan and I any of your questions on physics or whatever else. And to find that, just go to patreon.com/whythisuniverse. As always, thanks for listening.